Good afternoon, everybody, and welcome along to Data Platform Downunder for this session in April. Once again, my name is Warwick Rudd, along with Martin Catherall, my co-host. We bring to you this month Kevin Fiesel, who's going to talk to us about Does This Look Weird to You? An Introduction to Anomaly Detection. Now, this session is being recorded and will be uploaded to our YouTube channel within a couple of days of this session finishing, so that you are able to come back and watch this session and any of the previous sessions that we have on the YouTube channel at any point in time. Throughout the session, if you do want to ask a question, either put it in the chat window, raise your hand, we can have a look at that, and at that point in time can either come off mute and ask Kevin the question you have, or we can read that from the chat window and go from there. So without holding up any further, I'll hand over to Kevin and we'll get today's session rolling.
All right, thank you. That right there is a presentation handoff worthy of note. So welcome everybody to, it turns out the first time I'm ever giving this talk outside of my company. So I gave a version of this talk back in December internally. There are some things I can't talk about here, specifically about product, but got an action-packed session for you here about anomaly detection. So before we get too far into this, my name is Kevin Fiesel. I run a predictive analytics team here in Durham, North Carolina. I'm a Microsoft Data Platform MVP, and I have a blog called Curated SQL. The idea of Curated SQL is I like to try to find and link to 5 to 10 interesting posts per day on topics all across the data platform space. So it's curatedsql.com. What I want to do in this talk is give you an idea of what anomalies are beyond just a commonsensical, this looks weird to me type of explanation. We're going to talk about some techniques for reviewing anomalies. We're going to build a pretty simple anomaly detector using ML.NET, and then follow up with using the Azure Cognitive Services Anomaly Detection API to round things out for the afternoon. So let's start off with the question of what is an anomaly? And by the way, as Warwick mentioned, if you do have questions, I can see chat throughout this. That's also why I'm looking over this way. It's not because I'm trying to avoid you. It's just my screen's over there. But chat's right in front of me, which is how things should be. So if you have questions, do feel free to pop them in at any point. So what is an anomaly? At its core, an anomaly is something that is sufficiently different from the norm to a point that's actually of interest to us. So I can take this and say, yes, this is different, but it's not interesting. Or this is interesting, but it's not different. To be really anomalous, you have to be both, is what I'm getting at. There are, however, several conceptual definitions of what makes for an anomaly, and we're going to break them into a couple of different categories. I'll give you some general concepts. Again, this looks weird to me, and I'll justify why this looks weird to me actually is a reasonable explanation for an anomaly. Then we'll talk about some technical definitions for when looking weird just isn't quite enough. Okay, the non-technical definition. There is an anomalous element in this image, and everybody's already seen it. I don't even have to look over to it, point it out. I don't have to say anything about it. You've already seen that's the weird one. And this can get a little muddled at the edges, meaning that you can be tricked into thinking something is anomalous when it's not, or isn't anomalous when it really is. But on the whole, we're pretty good at pattern matching as humans. It is an evolutionary strength of ours, and we have developed this over quite a long time to pick out things which look dissimilar. So we're going to be able to take advantage of that. Getting into some of the specifics around this, you get into the Gestalt school of psychology. And this psychological concept or set of concepts is that our minds are pattern matching instruments. So we receive visual input information, we process that information, and the brain essentially figures out what pattern this visual information falls into and ignores the rest. Sometimes to a funny extent, where you can very easily trick a person by showing them something that their brain fits into one pattern, but really fits into a completely different pattern. Or where we're focused on one thing and completely miss the other thing. There's a funny YouTube video about basically you're watching people dribble a basketball and pass between them. And the question is, how many passes do you see through this? And the point of the video is that in the middle of it, a man walks in wearing a gorilla suit, and he's wandering around, just walking around as people are passing the basketball between each other. He walks away, and then the question is, did you catch the gorilla? And actually, a fair number of people never catch the gorilla because they're so focused on the basketball passes, their brain has filtered out any information which is not related to basketball passes. So it can be tricked. It's a fallible instrument, but there are a pretty good there's a pretty good understanding of how all of this fits together. So let's talk about a few principles of Gestalt. The first one is the law of closure. The idea here is that our brains will naturally see something that is 80 or 90% complete, finish the job, and say, obviously, that's a square. Technically, it's not a square. It's not closed. But our brain will do the closing for us and say, yeah, that's basically a square. This way, if something is very lightly covered in dirt, we don't get confused and say, well, that's clearly something completely different. It's like, no, it's an animal. It's got a little bit of dirt on it. It's still the same animal. The law of common region indicates that if there is a region, we will naturally group inside or outside based off of your position within that region. So we see two groups of blue dots. They're exactly the same blue dot. It was all copy paste, but because I drew a gray rectangle in there, we now think of it as two separate groups of blue dots. Figure and ground is an interesting one. And actually, I'd like to see people's perceptions here in chat. So what do you see in these two images? And actually, do you see different things in these images? And while that's going on, I'll talk about the concept, but I would definitely like to hear what you're seeing. So usually we prefer to see foregrounds over backgrounds, and we'll focus on a foreground image. There are exceptions to this. If you have, say, bokeh, where you're purposely fuzzing the foreground, yeah, we're going to look at the background. If you see sharp color contrasts, we're going to focus on the color contrasts. But there are some exceptions, and this is called Rubin's vase. So Martin actually sees what I think a lot of people normally see, and Mike mentions seeing both of them in both images. A lot of people will see the dark coloration in here, and that's what they'll pick out first, that the first one is a vase and the second one is human faces in profile. And it's actually the same image, I just palette swapped, but our brains do an interesting job of kind of emphasizing that based off of color contrast, probably due to, in part, to my slides, you might see one thing in one image and a different thing in the other image. So it's, again, a way that we can trick the eyes, but it helps us match patterns really well. Proximity states that when you've got things that are part of the same grouping, they will be in physical proximity to one another. This is where we get a lot of our intuition on anomalies, that we have things over here and then the thing over there. And we naturally cluster things together based on that proximity. So we see the 3 dots on the left and the 1 dot on the right, and a couple of clusters in between. Similarity indicates that based on aspects like color, shape, size, we will naturally group things together. So here I've differentiated things based on color, and naturally we will group things together and say, oh, all the blue dots, all the gray dots, all the yellow dots, those must be the same thing or of the same class, because Otherwise, they would have different colors. The coloration means something. It is indicative of something. Continuity is an interesting one here because mentally, this looks weird. Because what we want to do, if I did this just strictly in black and white, we would come down the curve and then we would have this straight line right here. And our brains would look at that and say, well, obviously you have a straight line and a curved line. But because I introduced color, you have this disconnect that is a little uncomfortable to look at. I mean, it's not like unbearable or anything, but all things considered, if you had this as one color, not many people would think of this as a couple of sharp curves. Finally, we do tend to simplify complex shapes. So if I show you the thing on the left, you usually will try to decompose it and say, oh, that looks like a triangle, a circle, and a square, as it does on the right. So our brains attempt to match shapes to patterns and to take something that it hasn't seen before and attempt to break out things into what they probably are. Again, this is really helpful when, say, you're trying to pick out a predator on the savannah or a snake in a tree. So kind of helpful in that regard. All right, how does all of this apply? Well, going back to the idea that humans are natural pattern matchers, we're going to take visual inputs and try to apply heuristics to them. And we generally do an okay job of it. We can be tricked with optical illusions, but we usually do an all right job of it. So here I have an example of yards per game passing versus points scored in 1 week of National Football League football. So if we look at this, we would say, yep, it looks like there's a pattern that the more passing yards you have, the more points you score, and that there are a couple of oddities down here. Now, whether that's anomalous or just that we have a fairly broad distribution, we could discuss that. But we're able to make that pattern. We're able to kind of mentally impute that there is a line somewhere around here. Maybe it's there, maybe it's a little lower. That's something we'd have to talk through. But we can see that there is a correlation based on these data points. We could fit a line to that, and this ends up being the best fit line here. And do make us wonder about those outliers down at the bottom. So I've used the term outlier. In this case, what I'm saying is we have some distance, a significant distance from our plotted line, our expectation of what reality ought to look like. And the question would be, if these are outliers, should this line really be pushed up a little bit? Well, if they're really outliers, maybe. But perhaps these are just a few points out of a very large number, and that the real distribution, instead of a really nice thin line, we have this fat curve. That could also apply. So not enough information, but at least we have something that we could look at. Now, this can get us some of the way there. But if we really want to apply anomaly detection to a practical problem, we're going to want to go further than I can see it with my eyes. Because in many cases, we may see an anomaly that actually isn't anomalous. It's just we may not have enough data to understand that it's not anomalous. Other things may look normal, but actually are anomalous because they, say, violate some precept that we didn't take into consideration or that we couldn't really see in the curve. If I move a dot just a little bit, it may be enough to indicate to our brain that, oh, well, this is close enough, versus if I move it just a little bit further, oh yeah, this is now off. So we have those mental points where we can fudge it a bit. And that's where I want to drive to technical definitions. And there are several technical definitions. Here's an example of one, which is anomalies on a fitted distribution. So in this case, I've simulated a normal distribution, and normal distribution basically says that I have a mean of 0. So mean of 0, a standard deviation of 1. So consider that somewhere around there. And that therefore, if you follow this distribution along, roughly 68% of the values will be within that range of -1 to 1. 95 will be -2 to +2. 99.7% will be -3 to +3. Now on here, I have some values out here at, let's say 7, I'll call them 8, 9, somewhere around there. And to give you an idea of this, we're now talking about you have roughly a 1 in a trillion to about 1 in a quadrillion chance of seeing a point that far out. So I had maybe 1,000 data points here, and I pulled several 1 in maybe a quadrillion. If I saw this in real life, I would say that looks weird. And according to a normal distribution, we can say, yeah, it is extremely unlikely that you'll find 3 data points that far out for this few for this small of a sample size. And it may be enough to question, is this really a normal distribution? Because if it's not a normal distribution, then we have to rethink what the probability is that we see something like this. In reality, I fudged those numbers and changed them such that we would see a bump. But this is a case of, yes, this is anomalous because there's a sufficiently small percentage likelihood that this could happen, that when we see it, we can be suspicious. Looking at this from another perspective, here is a box plot. So the idea of a box plot is that we're going to capture information about some variable. Like in this case, it's the number of invoices broken out by month and year. So I've got all the invoices in 2012, all of the months of 2012, each of which is a data point, and going up to 2018. So the line here is the median, or the 50th percentile. Half of the data points are at that level or above, half of them are at that level or below. The box represents what is called the interquartile range. So the top of the box is 75th percentile, bottom of the box is 25th percentile, meaning that I've got, in my case, 6 out of the 12 elements, the middle 6 of the 12 elements within this box. Then the lines represent up to 1.5 times the interquartile range. So the whole idea here is I take this box size, multiply it by 1.5, and kind of stack it on top. And I find the low or the highest point that is below where that would be. And I say, oh, well, it's right here. This is my whisker. So these are all of the other elements. If you go past 1.5 times the interquartile range, you have an outlier. So this is another technical definition of what constitutes an outlier. You see the interquartile range, and you go far enough beyond that in either direction. You say, well, it's uncommon that we're going to see something this far out. And as you can see here, we have a couple of points that are drastically lower than what we would normally expect. And they could be perfectly reasonable explanations for both of those. Could be that there's an issue with the data. I can't tell you why the number is low. I can just tell you that the number is low to the point that it might be worth investigating. And if I see a huge number of anomalies, that tells me, actually, based on the law of proximity, that's an indication to me that if I see so many anomalies, it's not really anomalous. It's just we're looking at this wrong way. So seeing just a few outliers, that's an indication that, yeah, I may have something to investigate, to at least understand why. Another example is with a process control chart. So the idea here, and I'm going to draw the lines just in case you have difficulty seeing the gray on the screen. So this gray box in a process control chart represents normal. And think of this, for example, as you are machining parts. Maybe you're cutting metal with a router, and you need to have wells that are exactly this many millimeters wide and this many millimeters deep, and you have a certain tolerance. As long as you're within that tolerance, everything's okay. Once you get outside that tolerance, things go bad. The machined parts may not be useful anymore. It could indicate that there's some sort of failure with the router. So we have this line, and we can see that there are a couple of points that have moved outside of the line, and those are indicative of a problem. So in this case, I need to fix my slide. So ignore that text. That text was for a previous slide. In this case, what we're seeing here is that a process was in control, which is the phrase when you're within that gray box. It was in control for a while, and now it has gone out of control. And if we are talking about a routing machine or some sort of, say, woodworking or metalworking equipment, this is where a trained technician may look, see the results, and say, uh-oh, here's what the problem is likely to be. Here's how I can fix it. So as we move on, talking about data set considerations, if you do have questions, now is a great time. Great time for me to take a drink as well. So let's talk what makes a data set good for anomaly detection. When you're on your anomaly hunting expeditions, we do want data sets that follow certain properties. Ideally, we're going to have one numeric feature that we try to measure. The more features you introduce, the harder anomaly detection becomes. The more you have to worry about how the features interact with one another, and the harder it is to track differences. You can still track differences. It just becomes harder. Ideally, you've got at least 30 data points, preferably 60 to 90 data points. The rule of thumb about 30 data points is exactly that. It is a rule of thumb, but it has a basis in statistics, and it's reasonable enough. Ideally, I want to have 60 or 90 plus data points, because that's going to give me enough, hopefully enough information for my single numeric feature for me to follow along and understand, is a thing actually weird or is it just uncommon? And ideally, we have at least one full cycle of behavior, and preferably 2 cycles or 3 cycles. So what I mean by this is that if I tell you about the sales of beach umbrellas in the month of in one month versus another, I was going to say specific months, but then in Australia, the example would be almost the opposite. So if I have beach umbrella sales in winter months, and then I pull in a data set that includes information about summer months, I could say, oh, this is an anomaly. This is uncharacteristically high, when it turns out that no, beach umbrellas are just a very seasonal purchase. You don't tend to buy them when it's cold. You tend to buy them as it warms up. So as a result, we want to be able to track, say, an entire year, because we need to capture that seasonality. Ideally, we capture 2 years or 3 years of data, because then we get seasonality, but we can also understand the overall trend if things are generally, you purchase more of them over time, or people are purchasing less of them over time. So to separate that out from the seasonality, we need several seasons. Whoops. So is time series data required? Betteridge's law of headlines is something I love. Basically, if you've never heard of this before, Betteridge's law of headlines states that if a headline has a question in it, the answer is usually no. And in this case, the answer is no. Time series data, however, is used very frequently when tracking anomalies because we tend to care mostly about temporal anomalies. That router that has gone out of control, we want to know when it happens, and we want to know when it stopped happening and when a technician fixed it. There are times, however, when we can look at data that's within what I'll call the same cohort or within cohorts in a given time frame. And actually, I showed you an example of that already. This was data captured from 1 week of professional football. And it is, I would consider, a reasonable example of what we could do in terms of tracking outliers, because I can, in fact, plot a line. I can look at what the distances from that line are for these data points, and I can estimate that the 2 data points at the bottom are probably the furthest away from the line and drag that line down considerably. So in this case, yeah, I can absolutely do outlier detection on non-time series data. Now, the assumption here is that all the members of the cohort have the same operation function. So what I mean by that is that if we expect that there's some sort of correlation between yards passing and points scored, then I would expect that all of the data points in this have roughly the same correlation. And that can be a reasonable guess if you're saying, I want to collect data from people playing professional football in the year 2020. But if I include elements from, say, 1992 and 1974, well, the rules of the game were radically different for those 3 year combinations, and the data points will look quite a bit different. So the operation function wouldn't be the same, and we'd have a lot harder of a time tracking if something is actually anomalous. In 1974, there was not nearly as much passing, so we would see a completely different curve. How do we track these anomalies? And as we're doing that, I'll take a quick drink and allow this question to come in. Building up the drama, the tension. We're all counting on you, Anil, or Anil Kumar. As we get to tracking anomalies, there are quite a few techniques, so I want to dive into those as we get there. But if anybody else has questions during this time as well, great time to put them in chat or even come off mute. Oh no. Oh, okay, we're back. All right, I will move on while you folks are typing in chat. That way you don't have to watch me watching you, and then it gets awkward. Let's talk about some of these anomaly detection techniques. How long do we track anomalies on a large timeline? The short answer is however long you have the data for, and as long as you expect that, again, that operation function is roughly the same. So some of these techniques here, we'll actually look at them being more of window-based, and some of them are based on the whole data set. But usually, if you're talking time series, which you mentioned timelines, quite often in time series, we're interested in what happened now versus what has happened recently. And we heavily discount things that happened a long time earlier. So in an example, perhaps we're looking at the number of items sold. So we look at the number of items sold by day and factor out any seasonality. Then we're going to track that and say, was the number today radically different from the last few days? And care a lot less about, was it radically different from 2 months ago? Because if we have, say, a constant gradual downward trend in the data, then this point down here and this point up here, yeah, they're quite a bit different, but we've got a lot of points in between that kind of take us to there. and therefore it's not really anomalous. So proximity matters a lot. We get back to that law of proximity, that the data points that are closer to you, you should be closer to them. And if you are radically different from one of those data points close to you, it's likely you're an anomaly. So we have dozens of techniques available to us. You can hit the research papers, you can dive into quite a few different possibilities, but there are commonalities among most of these techniques. And one of them is that, actually what I was getting at here, points that are clustered near each other are less likely to be anomalous. Meaning, going back to that law of proximity, if I have one data point that's in a zone and nothing else near it, that might be anomalous. If I have dozens or hundreds of data points near it, it's probably not anomalous, even if dozens or hundreds is out of 100,000. It's still enough that we could say, well, it may be uncommon. It may be, it may be uncommon, but it's not necessarily anomalous in the sense that it is actually weird. It's just, it happens too frequently to be truly weird. There will, in pretty much any data set, be a few outliers. In fact, actually, one of my rules of thumb is if you have a data set with no outliers, I'm more suspicious of it than a data set which has outliers. If you show me something with 0 outliers, I'm going to start from the assumption that this is probably fabricated data. It's actually a fraud detection technique as well. When people are attempting fraud, they will quite commonly try to fudge things so that nothing looks weird, because you don't want someone to take a close look at it. But when nothing looks weird, that is weird. Anyhow, back to this talk. It's a whole another talk on fraud detection. But there will usually be a relatively small number of outliers. And the idea in most of these techniques is we can isolate those. We can look for distances and assume that there's a relatively small number of things we have to do closer checks on. If we had to do a thorough check on every single data point, there's not enough time in the day for that. With time series, going back to the question about timelines and my point of proximity, within time series data, from a point to point, the changes should not tend to be very drastic. There will be variance. There will be ups and downs. You may sell 1 of a product today and 10 of a product tomorrow and 3 of a product the next day. That's not necessarily anomalous if your normal variance is that you sell between 0 and 15 on a daily basis. So there is some scope for predictability. So is only a sample enough, or do we need the whole population? What about in the case of real-time data? So getting to the core of the statistics, yeah, you can sample for sure. And that's where I wanted at least ideally 60 to 90 data points. If you're talking about within proximity, the window size can be a bit smaller, but I do want to have a total length of at least 60 plus data points so that I can hopefully get some seasonality effects. I can hopefully get trend effects and hopefully get a feeling for where things are going, so that we don't accidentally mark something as an anomaly when it's really just helping set the trend. And what about real-time data? Oh yeah, you can absolutely track this on real-time data. Once you've trained a model, or once you have an understanding of the tools necessary to check if something is an anomaly, basically time series anomaly detection is real-time data that's backcasted. So you can do it on data that's just happened as well. All right, trends and seasonality. I keep talking about those. They are important. They do affect analysis, and we do have to remove them before we're able to perform some of these checks, because they will affect our likelihood of capturing a proper anomaly versus simply saying, yes, beach umbrellas sell better in the summer. Next, let's take a quick detour about standard deviation. If you've if you're not familiar with standard deviations, or you blanked out all those statistic courses from college, standard deviation is a calculation of variance. Technically, it's a square root of variance. So the idea here of what standard deviation does for us is it tells us how widespread a set of answers is. In my case here, I have 3 separate job satisfaction ratings. In the first one, this blue line has a mean of 50. The red line also has a mean of 50. Green line, not surprisingly, mean of 50. So the average score for all 3 is the same. But for the blue line, the blue curve, the standard deviation is 5. So 50 plus or minus 5 gives you 1 standard deviation. And if this is a normal distribution, that's 68% of your data. So 50 plus or minus 15 gives you 99.7% of the data, meaning that for this blue curve, assuming these are normal, 99.7% of data elements sit between 35 and 65. So if somebody comes in with a score of 100, that's very uncommon. That's very unlikely. And that might be worth investigating. Mind you, the fact that something is an outlier does not mean that it's wrong or that it's bad data. It could just be that it's so incredibly uncommon, yet still true. So it could be that despite 50 being the average score, there is the one person who gave 100. Now, by contrast, with this green curve, the standard deviation is 20. So basically 50 plus or minus 60 is your 99.7% range. And actually, if your score cuts off at 0 and 100, can't go that far out. But essentially, we'll say that there is no value in this range, which is truly weird, according to a rule of thumb of 3 standard deviations past the mean. So the wider your set is spread, the less likely or the further out you have to go to find anomalies. It's a fairly intuitive explanation. It's a fairly intuitive thing that we could understand, but it's worth thinking about. Now, there's a problem with standard deviations. And I'll get to that problem actually on the next slide. Here is where I keep getting at 68, 95, 99.7. So these are for a normal distribution. Other distributions will not necessarily follow these, but large enough data set samples tend to follow, they tend toward normal distributions. Generally, there are exceptions. There are certain types of distributions that will never actually approximate normal, but many of them, if you get enough data, will get close enough that you can at least fake it. But here's the downside to using standard deviation. It's very sensitive to a single outlier. So I have an example. If I have some values that range, you can see from 7.3 up to 9.6, the standard deviation of this set is 0.85. You can plug those numbers into SQL Server if you'd like. You can plug them into whatever you'd like to. You'll get 0.85. You'll see a mean of 8.65. So if I tell you a value like 5.1, then we'll say, okay, well, 0.85 times 3, I'll actually do the calculation, says 2.55. Minus 2.55 is 6.1. You can see you can check my math. So 5.1 is more than 3 standard deviations away from the mean. 5.1, if I saw that value, would come up as this is a little weird. However, let's throw in one more value. Let's say we do have a real humdinger of an outlier, 1.9. Adding this 1 value will change our standard deviation. It will triple the value. It will more than triple, and change the mean by a full point. So now 5.1, if I drop that value in, it no longer looks anomalous. And, you know, on net, it's not a bad thing. I mean, this is getting to one of the core insights of the Bayesian approach, that as you get new information, you change your understanding of how things work. But this is kind of changing to an extreme. And as a result, there's been quite a bit of research on the concept of robust statistics. The idea of a robust statistic is that it can handle a limited number of outliers without breaking down. So the alternative to looking at standard deviation is called MAD, median absolute deviation. And the idea here is that you take your specific value, you subtract the median from it, take the absolute value of that, and you get the median of all of those differences. So take our initial data set. Our median is 8.75. Again, if you don't remember how to do this, basically, here's the way the calculation works. First, it's like prison rules. You find the biggest, meanest, nastiest number, and you shank it. Then you take out the smallest. And you repeat that process until you have either one value left or two values left. Because I have two values left, I'm going to take the mean of these two values, and therefore my median is 8.75. The MAD is, what is 9.1 minus 875? 0.35. And we go on and on and on. So our MAD is 0.55. Now, let's throw in one crazy anomaly. This thing's way different from everybody else. What this does to change our median is that we, again, start with the biggest, meanest number, and then we take out the smallest number. So you'll notice our calculation for MAD just throws out the extremes on anomalies and will leave us with something that is a closer value to the middle. So our median shifts a little bit. We learned new information, but we didn't radically change. And the actual calculation of MAD, even with this crazy 6.5, is still just 0.9. So 5.1 would still be considered an outlier even after we had one anomaly. The other nice thing about MAD is that if you have some anomalies in both directions, they will cancel each other out. So MAD breaks down when you have a lot of anomalies in one direction, but if you have anomalies in both directions, larger and smaller, then essentially they'll cancel each other out and the formula will work better than something like standard deviation, which compounds as you have large outliers and small outliers. It just stretches out further and further. So something to think about, calculating MAD instead of standard deviations. Another thing, suppose we've got a trend that has an anomalous jump. So here we pretty clearly have a trend, but then we have these data points that are quite a bit above the trend. So what I want to do is separate out what of this is the trend versus the anomaly. And the way that we do that is that we find the trend and we detrend it. So first, fit the data with a line. And you'll fit the trend data with the line. I'm excluding these jump points from this line. And then you essentially rotate the line. You subtract the value of the line, leaving only the value of the anomaly. So now we have that flat line and we can calculate vertically what the distance is. And this vertical distance is now the amount of the anomaly. And that's called detrending. That's a geometric explanation of the process. This is extremely common when you're working with time series data because you will have changes. You'll have those trend level changes, and we want to avoid those. Now, another bit is called change point. A change point is an abrupt shift in time series data. I mentioned that law of proximity. things that are close to each other, we expect to be pretty similar. And with time series data, think about you have a souped up sports car that you're racing on a track, and you keep track of acceleration, velocity, and distance. Well, if you think about the millisecond to millisecond differences, as you're accelerating, you're starting your burn there, you will tend to have numbers that are pretty close to each other. They will increase, they will move upward, but it's not like you're going this fast one moment and then a quarter of the speed the next moment and then 3 times the speed the next moment. It's more of gradual ups and downs. So change point detection says, well, what happens when we don't see a gradual change, when we see a radical change? Then this is a change point. And a change point could represent something new. We have a new operation function. So it used to be down here, but now it's jumped. So for example, our beach umbrellas, some celebrities buy these beach umbrellas and swear that they're the best thing ever. So previously our sales were down here, but now thanks to all the free endorsements, we have a lot of new people who've heard about our umbrellas and we're able to sell more. So this is a change in consumer tastes. And that change may be drastic, it may be abrupt. And if so, we'll capture it here. It is anomalous. And again, anomalous doesn't mean wrong or bad or incorrect, but it does mean this is changed in a way that is sufficiently different to be of interest. Another technique that we can use is to do all of this stuff that I've talked about, but not on the numbers themselves, but actually the differences. This is also really good for time series data. So if I'm looking at what my data point, what my time is right now versus the previous time period, then I may capture the difference between those two and look to see if there are oddities there. So here I have pretty clearly a jump. And what you can see in the differences is that at the beginning, we're usually within about this curve, but then it spreads out a bit. So we can see that the jumps here also come with essentially an increase in variance between data points. Tracking these differences over time, difference analysis, can give you information on anomalies that you may not have caught when looking at the actual values. Let's build out an anomaly detector in 144 lines of code or less. When it comes time to look at anomaly detection, there are quite a few pre-written packages, and I do recommend that you start with one of those. There may be reasons to build your own. My team actually did build our own because we wanted to do specific things that weren't available in some packages. But if you're in R or Python, there are some really good packages. Anomalyes is a great solution. Profit's a Facebook package for time series analysis. It's an okay package. I have my concerns with it, but mostly in terms of how well it works or doesn't. But I have a link here for time series analysis. So somebody who's done some time series analysis based off of the Profit library. Twitter put out their anomaly detection library about 5 years ago, and that may sound like a bad thing, but frankly, a lot of anomaly detection isn't exactly new. A lot of the research, even on robust statistics, that was coming into vogue in the 70s and 80s. So there's quite a bit of literature that has been established on what makes for good anomaly detection techniques. And as a result, the fact that a package is a little old or hasn't been updated lately isn't necessarily a problem. On Python, there's an anomaly detection toolkit as well as PyOD, And in the .NET world, we have ML.NET. I also include Azure Cognitive Services, which has a REST API. So anything that can work with a REST API, you can use Azure Cognitive Services. If you do want to roll your own and you would like to use .NET, I highly recommend the package called MathNet. Actually, it's a series of libraries for numerical and statistical analysis. It'll let you work with either C# or F# code, and there's a lot of functionality that's built in that allows you to do essentially one-line operations for calculating MAD, calculating interquartile ranges, that kind of thing. And our team actually does use MathNet for some of this work and can calculate things like these. I'm being kind of vague about exactly what's included because I don't know how much I'm allowed to say about what we do for anomaly detection, but these are the sorts of things based off of techniques we talked about, which would be a good idea to look at. I'll leave it at that. What about love for Excel? Excel is, it always will have a fond place in my heart. There are a lot of positives to Excel, and if you're in a regulated industry, you may have to use Excel because of just how difficult it is to handle getting approval for your new product. So you'll see actually statistical toolkits that were written in Excel because, for example, the US FDA, Food and Drug Administration, approved this particular set of tools for Excel 10 years ago, and it's actually easier just to use that than to try to fight the FDA and get a new package recognized. If you're dealing with moderate-sized data sets, I like Excel a lot. Once you start dealing with really large data sets, or if you want things, like close to real-time data coming in, or multiple people interacting with the data, then I would probably push you somewhere else, and that would be toward R, Python, .NET, something closer to that. And speaking of .NET, there is the package ML.NET, and this has some anomaly detection capabilities easily accessible within the product. This is actively developed by Microsoft, supports both F# and C#. Their F# support is not fantastic, but it's there. Now, let's say you want to build a .NET package, you want to detect some anomalies. And what you're going to do, create a new console, choose your language. I've chosen F#, and I've named it Basic Anomaly Detection. Inside there, I'm adding two packages, Microsoft.ml and Microsoft ML time series dataset. I'll also add the xplot.plotly package to visualize data. And with that, let's hop into a demo. Incidentally, as I go through the demo, if you have some difficulty seeing this, if it's too small, let me know. I'll bump up the font size. But this code, basically we're loading up our packages, and I'm setting this class, or in F# terms, a type, called price data. So where does this come from? This is a data set of the greatest stock ever, GameStop. And we want to capture just how diamond-handed people are. So I have from 2020 up to 2021 in April, I've got the opening price, high, low, closing price, adjusted close, and volume. I'm going to focus here on close per day. So this value, like on April 13th of 2020, it closed at $4.74. And we'll check to see if there are any anomalies in the GME data set. Spoilers, there are. So we have a class that basically defines these are the inputs for that text file. And we're going to load the GME text file using what is called a ML context. So this is ML.NET's way of interacting with the outside world, building out a data view. So that data view is of the shape price data. It's located in this path, gme.csv, and lets us take that data in pretty easily. There are similar functionalities in R and Python, and .NET attempted to make something that was close enough for data scientists to where you didn't have to build an entire ETL style process within .NET to load a text file. Okay, we're looking for anomalies, and we look at a history length. And change point history length of 10 days, anomaly of 30 days. This goes back to the point of how far back can we look, or when we're looking at data. And this is basically saying we're going to take looking at one day, we're going to look back 30 days and see, was this really anomalous, or is it just part of a trend? And for change points, we're going to look back in the last 10 days. Was this data point apparently a new change? And each day that we look at, you can think of this as it is still real-time data. So if I have new data feeding in constantly, the algorithm processes the same way as it would with this data set that is static, that has already happened in the past. As long as your application can keep accepting new inputs, you can continue to plot, you can continue to determine whether there are anomalies. It's going to involve more code that you write on your side to make this a more stream-driven feature, but conceptually, it's right there. And actually, there's probably an easier way that we'll get to with Azure Cognitive Services. Okay, so we've got some pipelines for anomalies and change points, and I'm going to fit them. The last, say, 60 lines or so is really just showing you a pretty cool visual. So I'm not even really going to dive into what that code does, because most of this, basically, once you get down to roughly line 98, at this point, this is all collect the data in a way that we can visualize it. And I'm going to run this application, and it will pop up Plotly for .NET. This is specific to F#. And what we see, green points are change points, yellow or orange are anomalies. So this is GameStop's stock. Starting in 2020, it was down in the $4 range, and roughly about mid-January of 2021 got hot, and it peaked at somewhere around $350. It actually, I think it hit just shy of $400 at its high value, and then there's some weirdness, and it dropped back down into the 50s and 40s, and it jumped back up again, and it's bounced around. It's now somewhere in the $160 per share range, but quite a bit of jump over a year. I can zoom in here and see it looks like there are a lot of anomalies in this, and this kind of gets to when you have a fairly stable price, like here you can see it always ranges $3, $4. Even a relatively small change can be considered an anomaly. But then we have the real anomalies, and basically like every day in this range here is an anomaly. But what's interesting is you don't see any at the end. And part of that reason is once you basically have $300, and they jump around $70, $60. Once you're establishing that this is normal, or this is happening often enough, the anomaly detection algorithm looks at it and says, well, over the past few days, I mean, you had data points that were down here, so this isn't necessarily anomalous. We do have a change point here that says, oh, we're going back to crazy town. And then it's dropping down again. So looking at this, we see, oh, there are anomalies, but they're not necessarily, at this point, it's expected. Okay, briefly, using Azure Cognitive Services Anomaly Detector, because I know folks have to get back from lunch. The API for this allows you to perform anomaly detection from any language that supports hitting a REST API. And we've got a few steps. Create the anomaly detector resource in Azure, save the key and endpoint in an environment variable or something like that, and create an application to work with the API. So creating this thing in the Cognitive Services Marketplace, you just search for anomaly detector and you'll find it. And the anomaly detector creation, I want to point out the pricing tier, that there is a free tier for anomaly detection, 10 calls per second, 20,000 transactions per month. For testing stuff, for playing around with it, that's plenty. Then you create your endpoint, you go to the keys and endpoint, you can copy your keys, you can copy your endpoints. And I used setX to set an environment variable locally. Once I've done that, I'll be able to use the application. Here I can check out the Anomaly Detector API demo. So this is the Anomaly Detector API. It is available at algoevaluation.azurewebsites.net. I have a link to that in my notes. And let's bump this up just a little bit. The one downside is that you do need to show off an endpoint and a key. And I'm going to show you my key because I am confident that nobody here will use it. Also, I'm going to change it pretty much as soon as this demo is over. So let's choose the entire API. I'll choose sample 3 with seasonality, and I can select start. And it pops out and says, okay, well, you had one anomaly down here. That's kind of a boring example. Let's look at this one. Here we've got something that's got anomalies. So I select start and it says, hey, you've got anomalies here, here, here. You've got some over here. So you can see what the result looks like. You can see that it was pretty fast. It came back very quickly. And you can also see that there was a minor trend change that was not captured as anomalous. For people who are interested in more of real-time stuff, you have this last API. And what I'm going to do is let it run for just a moment to give you a feeling for it. Basically, it's looking at each day, and it's going back the gray window size to determine was this an anomalous date or not. What's interesting is that the entire data set test will actually give you different results from the window data set test, because here the window is only looking inside that gray box versus the entire set is looking at every data point. So you may see points that show up here which aren't necessarily in your other example. I'll stop that for time's sake and talk about the API. We do have libraries like ml.net, and frankly, I would probably use that rather than Azure Cognitive Services if I'm writing a .NET app. But if you have the Cognitive Services API, we can roll with it. We can create a project that creates a new console app and loads up the Cognitive Services Anomaly Detector. I'm also loading f#.data to read my data set. And that gives me a different project. So let's close these. And what I have is loading in data from a different gme.csv. This is actually a smaller data set. That way I don't hit the Cognitive Services API with too many data points at once. I use the Anomaly Detector client syntax to create a new client, sending in my API key. Oh, by the way, let me regenerate key 1. Okay, there we go. New API key using the key and the endpoint that I have stored as environment variables. If I come down here, I actually make note that you do have to set these before you could run this code. So you set your values, you get these values, and we create a client, we generate a request. Request generation says load up the text file, and for each line in this text file, create a point using the date and the closing value. And then turn this into a request that the anomaly detector client can use. So I have a list, it's actually a C# friendly list, and a granularity that says this is actually in the daily grain. So I have one data point per day. Then I'm going to try to detect this entire, run an entire data set detection. So I will make this attempt to call entire detect async, which is a method that's on the library. So client.entire detect async, wait for it to finish. And when it's done, I take the results and combine them with the series data. In F#, the zip function, basically think of it as I have data points and it's almost like a zipper coming together. So first comes to first, second to second, third to third, fourth to fourth. It's not a join because we're not joining on anything. Instead, it's just straight up first row connects to first row, etc. If I have anomalies, I'll print out how many anomalies there were, and then I'll print the specific anomalous values. So if I say go into Azure Anomaly Detection, .NET Run, I've already built this package. It detected one anomaly on March 24th. So I can go back, look at the data and say, oh, on March 24th, well, on the 23rd, it was $180. On the 24th, it was $120. And then it jumped back up to $180. That, by the way, really happened. And that is weird. It's weird that you drop down $60 in one day and you go up $62 the next day. All right, wrapping things up. Over the course of this talk, we've looked at this concept of what is an anomaly, dug into some of the psychology around it, learned some techniques for detecting anomalies, and finally, a couple of .NET packages, which make it pretty easy to do. If you'd like to learn more, grab the slides, get the demo code, links to additional resources, go to csmore.info/on/anomalies. If you have any questions, please do feel free to hit me up via email or Twitter, and I'll drop these links into chat so that if you want to grab them, they're there. And Twitter, if you're so inclined. I get on Twitter about once a week, it seems like. So with that, if there are any questions, I'm happy to take them. Otherwise, I appreciate your time this afternoon.
Thank you, Kevin. Thank you, everybody, for coming along. It was a very insightful session. So yes, as Kevin mentioned, if you do have any questions, feel free to come off mute or put them in the chat window, and we can have those questions answered now. For those of you who don't know, so for next week, just while we're giving time for people to put their questions, next week's session, we have SQL Server Internals and Architecture from Kevin Klein, same time. So if you haven't already registered, make sure that you do register. As mentioned at the start of this session has been recorded and will be made available on the YouTube channel within the next couple of days once the recording has been worked through and uploaded. So if we do have any questions, time to ask them. Otherwise, I do say a big thank you to everybody for coming along. A big thank you for Kevin for giving up his time and presenting to us this month. Looks like we've got a couple of people writing, so I'll give you a little bit of time, or if not, take yourselves off mute and ask away. Looks like it's all big thanks to Kevin.
Finding anomalies in Bitcoin where data isn't available easily. Would that be a difficult thing? So basically, to the extent that you have that data, you could detect anomalies. Basically, the two concerns that I would think about, first concern would be the data that is collected, is that really a sample of the entire, say, the entire population, or is it a biased sample? Is it a subselection? And if it's a subselection, then that may not be as meaningful for drawing inference as if you had a fairly unbiased sample of the entire population that just happened to be kind of small. And quite often you'll see this with data sets where I went and got these answers because those were the easiest to get. Phone surveys are a classic example of this, where in the US, for a while, telephone surveys were all done on landlines. So if you owned a landline, you were likely to get called by people wanting to do surveys. And that worked out for a while until a whole generation of people did not own landlines. Like, I've never actually owned a landline. That means that people who do surveys simply by calling on landlines would miss me entirely. And if the characteristics of the people who don't use landlines are different from the ones who do, you have accidentally biased the sample. And frankly, yes, the characteristics are different. People who don't have landlines tend to be younger than people who do. So that's a risk that you would have to consider of the data that you have. Is it really representative? The other side, the other thing is, if you have enough data, you're okay. But if I'm thinking about Bitcoin, say, in terms of the price, the exchange rate of Bitcoin, the variance is enormous for that. So you may find some outliers, some anomalies, but when variance is that big, it can be difficult tracking proper anomalies, because, like the example of GME, once you spread so far, anything's in play.
All right. You're welcome, Mike. Very interesting topic. Glad that that could be answered for you, Anokuma.
Very cool. Thanks, everybody. Glad I brought back the horrible, dark memories that you all tried to repress of college level statistics.
All right. Well, looks like another wrap for another session. Thank you, Kevin, for coming along and presenting. Thank you, everybody. I look forward to seeing you all online next session.
All right. Appreciate it. Take care, everyone.
Thank you.